Hi, I'm Megha Daga. I am the Senior Product Manager here at Cadence Tensilica, and I'm here today to talk about sparsity. Sparsity, the presence of zeros in data, in weights, in neural network, and why there is a need to utilize those sparsities. So sparsity, like I said, it's the presence of zeros in these neural networks. Neural networks, when they get trained, there is an inherent sparsity which is present after the training. This inherent sparsity we have seen over a wide range of networks can range to somewhere around, roughly around 15%. So there are around 15% of zeros which are present in these weights. And as on the other side, talking about the activation, about the data, these data, when they flow through a neural network layer, let's say there was a convolution followed by ReLU, so on and so forth, then ReLU is a kind of layer which inherently creates lot of zeros. It introduces lot of zeros in the data. So this is where we get much more data, and we have seen on an average this to be somewhere around 50%, 40%, 50%. So this is inherent. Then we have also seen in the market, just by doing some light pruning, this can be further increased to some little values, and then something which is highly getting explored in the market today is retraining. And let's say by retraining, we are able to further exploit it to 35%, and on data it goes all the way to 60%. This is something which is becoming much bigger with the layers. For example, there are theories where they say that for LSTMs, the sparsity can go all the way to 90%. So much zero present in neural network. What to do? And are there ways to exploit that? Is there a need to exploit that? Certainly there is a huge need to exploit that. Neural networks these days are governed by two major factors: bandwidth. So there is a big need for bandwidth reduction, and performance. There is a big need for performance bump. As the fields are growing, as the application markets are growing, their needs and their demands are growing. And with those demands, they want to get more and more done in as small as possible. How do we do that? We utilize all this sparsity, these presence of zeros, for bandwidth reduction. So we need to have a way so that we are not loading any of the zeros present either in the weight or in the activations. And by not loading those weights, we can get a huge reduction in the bandwidth, and when there is reduction in this bandwidth, we are loading less data from the system memory into the local memory, and overall from a system point of view, it helps a lot in the power efficiency from a system point of view. It also helps in latency by getting it much faster, and layers which are data bound, for example in LSTMs and fully connected, which are data bound layers, I am now able to fetch more data and make it more towards compute bound. Going to the second aspect of it, performance. How do we use these for performance? Well, there are so many zeros. What's the need of multiplying for zeros? So what we need to do is, now we utilize both this weight and these activations, and don't do any MAC operation for the zeros present in these. So do only the MAC operation on non-zero weights and non-zero activations, which will lead to compute reduction. When there is a reduction in the compute reduction, you are able to get a much higher performance from what you have in your core. So a physical array size can give you a much higher throughput, a throughput which is 2x or 3x of what you are capable of doing from the physically present array. So there are two aspects and which are heavily getting utilized now, and we need to be more and more aware of and use them. And these are the two aspects which we are using in our latest generation of AI processors in DNA 100, and it works wonders in both the areas. So with that, thanks for watching, and check back next week for more information on Whiteboard Wednesdays. Thank you.